Now we shall learn what will happen if we place an electric dipole in a uniform electric field. So you know what a uniform electric field is and how we present a uniform electric field. A uniform electric field is represented by parallel lines which are in the same direction. So this is your uniform electric field, and for uniform electric field, the strength of the electric field is same everywhere in the electric field. So if we have at this point, the strength of the electric field is same, and here also the strength of the electric field is same. So now if we place an electric charge, say a point charge, in this electric field, suppose we have here a positive charge, now what will happen to this positive charge? Since this positive charge is placed inside this electric field, say E, then this positive charge will experience a force. So if a charge is placed inside an electric field, it will experience a force, and since this is a positive charge, the force experienced by this positive charge will be in this direction. Similarly, if we have a negative charge and if it's placed inside this electric field, then the negative charge will also experience a force. So suppose we have a negative charge at this point, then this negative charge will experience a force in the opposite direction. If you can recall, one of the properties of electric field lines is that the electric field lines is directed away from the positive charge and is directed towards the negative charge. So in this case, if you look at the field lines here, this is directed from this point to this point, so in this direction. So it means that here we have a positive charge and here we have negative charges. So that's why we have positive charges here and negative charges here. That's why positive will be attracted towards the negative charge and this negative will be attracted towards the positive charge, because this is away from the positive charge and towards the negative charges around here. So these two charges, they experience a force. As you can see here, this one is in this direction and this is in this direction. Now if these two charges, they are equal in magnitude and they are separated by a finite distance, then this will constitute an electric dipole. See, an electric dipole is a system of two equal and opposite point charges separated by a finite distance. So here we have an electric dipole and this is placed inside a uniform electric field E. So in this case, the positive charge experiences a force in this direction and the negative charge experiences a force in this direction. And say the electric dipole has a dipole length 2a. So this is the dipole length. And say Q is the strength of this charge, and here also minus Q is the strength of this charge. So here we have minus Q and plus Q. So I'll write it here. Plus Q, and the strength of this charge here is minus Q. So here we have an electric dipole of charge minus Q and plus Q separated by a finite distance to A, and A is the distance of either charge from the center of the dipole. Now the dipole length here is directed from negative to positive. So here your P vector, I mean the dipole moment, your P vector, I'll write it here, P vector. This is directed from this negative charge to the positive charge. So your P vector is directed in this direction. This is your P, this one P vector. And you can see here that the P vector, this one, it makes, let's say it makes an angle theta. Okay, so we place an electric dipole inside a uniform electric field such that the dipole moment, vector P, will make an angle theta with the direction of the electric field. So this theta is the angle between P and P vector and this E vector. So I'll just write this theta here instead of here. So this is your theta, angle between P vector and E vector. And let's say this positive charge is placed at A or B, or it's placed at B, and the negative charge is placed at point A. So we have this positive Q is placed at point B, and minus Q, okay, this minus Q is placed at point A. Now the force experienced by these two charges, by the positive charges, is given by F plus. And this force is equal to Q E vector. So in vector form it will be F force experienced by the positive charge is equal to Q E, and the force experienced by this negative charge, F say minus, this is equal to minus Q E. Minus here because this is in the opposite direction of the electric field. The electric field is in this direction, the force experienced is in this direction. So this F minus is equal to minus Q E, and F plus, this is equal to Q E. So this is the force experienced by the two charges of the electric dipole, and as you can see here, the force between them, they are opposite in nature. One is in this direction, another one is in this direction, but the magnitude is same, Q into E, and here also Q into E. So the magnitude of this, I'll write it here. So the magnitude of this force is equal to QE, and the magnitude of this force is equal to, again this is also QE. This is in magnitude. Okay, so if you can write this one also in this way, instead of putting this modulus sign, I'll just write QE, here also QE. And here also, instead of writing in this way, I'll just write this F without the vector sign or without the arrow sign. So here we have F minus. So this is the magnitude of the two forces. They are equal in magnitude, but they are in opposite direction. One is in this direction, another one is in this direction. Okay, so these two forces, they are equal in magnitude but opposite in direction. Hence, if we take the net force between them will be equal to 0, because they are equal in magnitude and opposite in direction. The net force will be equal to 0. So this electric dipole will not experience any net force. Okay, so here the net force, F net, here the net force will be equal to 0 because we have one as this one, QE. Then we have this is in opposite direction, so they are in opposite direction, you have to take the difference between the two forces. So hence this would be equal to 0. So here the net force is equal to 0, so the electric dipole will not experience any net force, so it will be in the same position. Alright, so here we have two forces which are equal in magnitude but opposite in direction, and they are acting along different line of action also. So here this force is acting along this line, and this force here is acting along this line. So see, they are acting along different line of action. So two forces which are equal in magnitude and opposite in direction, and which are acting along different line of action, these two forces, they will constitute a torque, and this torque will tend to align this electric dipole in the direction of the electric field. So if this dipole is placed in this position, so this dipole will experience a torque and it will be aligned in the direction of the field or along the field. So that torque will try to align this electric dipole in the direction of the electric field. And the magnitude of the torque experienced by this electric dipole is given by, we have tau here, which is the symbol of torque. So this is the torque experienced by the dipole, and this is equal to the magnitude of either force, which is QE, then into the arm of the couple, or the perpendicular distance between the two forces, into the perpendicular distance between the two forces, between the two forces. So this is the torque, magnitude of either force into perpendicular distance between the two forces. So here we'll have to see which one is the perpendicular distance. So what I'll do here is, I'll extend this line here, and this is perpendicular to this line. So let this line be BC. So as you can see here, this is the force, and this is also the force, and the perpendicular distance between them is this line BC. Okay, so here the perpendicular distance between the two forces is this line BC, and since this and this is parallel, this angle here also will be equal to theta. So instead of this perpendicular distance between the two forces, I'll write it as BC. So this is the torque experienced by the electric dipole, is equal to QE into BC. Now we'll have to find what is this BC. Using this diagram, you can see here that this is the perpendicular, this is the base, and this is the hypotenuse. So here we have BC, the perpendicular, in this triangle A, B, C. BC is the perpendicular, AC is the base, and AB is the hypotenuse. So using trigonometry formula, one of the trigonometry formula. Now sine of theta is equal to, I'll write it here, sine theta. This is equal to perpendicular, which is BC, by hypotenuse, which is AB. Now AB, this one is the dipole length 2A. So here instead of AB, I'll write 2A. So here we have sine theta. this is equal to BC by 2A, and upon cross multiplication, what will get BC? We bring this one this here, so what we have is BC to be equal to 2A sine theta. So this will be your BC. So here this BC is equal to 2A sine theta. Okay, so this is from the trigonometry formula. So instead of this BC here, I'll write 2A sine theta. Here we have 2A sine theta. So that is the torque experienced by the electric ball. QE is into 2A sine theta. Now this will be equal to, if I put this one here, or I bring this 2A this side, I'll get Q 2A E sine of theta. Now Q to A, this is your dipole moment P. So here we have, instead of Q to A, I'll write P, and I have E sine theta. So this is the torque experienced by the electric dipole, and this is in magnitude. So the magnitude of the torque experienced by your electric dipole, which is placed inside a uniform electric field, is equal to P into E sine theta. E is the dipole moment, E is the strength of the electric field, sine of theta, theta is the angle between the dipole moment vector P and the electric field vector E. So that is the torque, and this torque, it will tend to align this electric dipole in the direction of the electric fields. If the dipole is here, okay, this electric dipole, on placing the electric dipole at this position, it will be, after a while, it will be in this position. Okay, so it will try to align this electric dipole in the direction of the electric field. Now torque is a vector quantity, so we'll have to express this one also in vector form, and this can be done by making use of the vector product or cross product. Now if you can recall, if we have two vector A and B, then A cross B, this would be equal to, write it here, AB sine theta, okay, with some vector notation here and cap. So this is the cross product. A cross B is equal to AB sine theta with some unit vector and cap. Now this end cap, this is perpendicular to the plane AB and is directed either inward towards this plane AB. So here in magnitude, if you want to write just the magnitude, then the magnitude of this cross product AB is equal to simply AB sine theta. So which is similar to this one. You see here, this one, tau is equal to PE sine theta. So this is the magnitude of a cross product, and in this case the two vector will be P and E. So this, I can write this tau as the magnitude P cross E. This is the magnitude P cross E. So here the vector form of this torque, so in vector form, your torque tau vector will be equal to the cross product of P cross E. So this is in vector form. So from here we can find out the direction. We usually express this torque in vector form to find out the direction of the torque. So here we have to use the right hand cross product rule. So here P cross E. So here your P will be in this direction and your E is in this direction. So here, using this right hand vector product rule. We take the direction of your P, so your P is in this direction, right? And your E will be in this direction. So what I do is, I'll take P in this direction and I'll curl this one cross, as you say cross E vector, you curl it towards this E. So your P is in this direction, cross E, and you extend this finger as you curl this, like this, P cross E. So you extend P cross E. So you extend the thumb as you curl your fingers. So here we have P, then cross E. So my thumb is extended downwards. Okay. So your torque in this case will be downwards, or towards the plane of this paper, or plane of this board here. So your torque tau in this case, it will be directed inwards, perpendicular to the plane PE and inwards. So that is the direction of your torque. Now we come to some special cases. One is when your electric dipole is placed in such a way that it makes an angle, that your dipole moment vector P makes an angle 90 degree with the electric field vector E. So if you have this one, I will draw just the direction of the electric field and the dipole. So if your dipole is placed in this way, and this is the direction of the electric field, E vector. So in this case, your P vector will be in this direction. So here you can see P vector makes an angle 90 degree. So if your electric dipole is placed in this way, then the torque experienced by this electric dipole, the magnitude of it, will be P E sine of 90 degree, and sine of 90 degree will be equal to 1. So here we have P E. So this is your tau. So if it is placed in this position, then the electric dipole will experience a maximum torque. So if we place at this position, it will experience a maximum torque. Then if we place this electric dipole, say in this position, this is your E vector. So if we place this in this position, one is positive and one is negative. So here, this is positive and this is negative. So your P vector will be in this direction. So here the angle between them is 0 degree. So if you place your electric dipole in this way, then your torque will be equal to P E sine 0 degree. Hence sine of 0 will be equal to 0. So your torque will be equal to 0. So these are the two cases. One is when you place it at this position, you experience maximum torque. And if you place it at this position, which is already aligned with the electric field, your P vector is already aligned with the electric field. So in this position, your electric dipole will not experience any torque. So here we have the two cases. So that is for your electric dipole in a uniform electric field. So if you place an electric dipole inside a uniform electric field, it experiences a zero net force, and it experiences a torque as well. And that torque will tend to align the dipole moment vector P in the direction of the electric field